Hello everyone. In this session and the following sessions to come, we're looking at solving an image classification problem using a multi-layer perceptron model. We are going to make use of this particular dataset called Fashion MNIST. As the name itself suggests, we have this large collection of images which are your fashion related images or fashion clothing and apparel related images. So first, before we begin understanding more about the data, let's look at who has created this particular dataset and what is their primary intent behind creating this. So there's a particular organization called Zalando. So this is a large e-commerce platform, a fashion e-commerce brand within Germany. So this is spread across various countries. So this is a multinational brand, and this is a small entity within this particular organization called Zalando Research, who have created this particular dataset called Fashion MNIST with a primary intention of replacing the original MNIST handwritten digit data for evaluating any of the ML algorithms that the researchers create. So what is the primary purpose of MNIST datasets? Researchers across the various organizations tend to make use of MNIST dataset in order to benchmark the different ML algorithms that they are creating. They'll also use these datasets to rapidly prototype any of the algorithms that they design newly. So these are the primary two reasons on why researchers tend to use this MNIST dataset quite a lot. Fashion MNIST dataset, on contrary to your MNIST dataset, generally provides much more complexity during the training process. So MNIST handwritten digit data is very easy and it's overused currently because every researcher across the organization basically are trying to prototype their algorithms based on this particular data. And it is said that if the algorithm is not working on MNIST dataset, it's said that doesn't work on any other datasets as well. So that's the primary intuition behind it. And MNIST dataset cannot represent better on modern computer vision tasks. So these are the primary reasons on why the creators have come up with this new dataset called Fashion MNIST dataset. The structure of this particular data, that every image is now represented in the form of 28 by 28 pixels, exactly matching with what is represented in the digits data. Similarly, we only have 10 different labels, which again is matching with your original number of labels that you had in MNIST handwritten digits data. So they try to maintain the same structure so that any algorithms that are already built on MNIST handwritten digits can easily be recreated or retrained using this new dataset here. Okay. So the primary reason on why we are considering this particular dataset is for us to get well versed with all of these data science and machine learning concepts. Let's say that you would want to implement batch normalization and also look at implementing the dropout regularization in order to create a generalized model that performs well on different sets of unseen data. So this is your task. And in order to learn this properly, MNIST datasets are very much appropriate. Not necessarily these concepts. Could be any other ML or deep learning concepts. It's better understood with the help of these datasets. So this is a primary reason on why we are considering these datasets. Moving forward, we'll consider other sets of problems and try and solve them. Okay. It's not that we are confined to only this particular dataset. You can explore more on this particular GitHub page. Try and understand what are the different descriptions that you can find for a particular target variable. So the target variable clearly is multi-class in nature. So there are 10 different labels associated. So each of these particular label has got a description again. So t-shirt is associated with label 0, trouser with 1, pullover with 2, so on and so forth till ankle boot with 9. Okay. So you can actually load this particular dataset with existing Python built-ins. So you need not externally download the complete data and try to read the complete data image by image. It's not necessary to do that. So there's a particular package called Torch Vision, which we are going to leverage in order to import this necessary class called Fashion MNIST, which is going to help us load the given dataset. The primary step or the very first step that we are going to take here is to create the dataset and DataLoader objects. So dataset and DataLoader objects are going to help us read the given data, read the XY data batch by batch. Where while creating the DataLoader object, you will define what could be the batch size. All of this we already have implemented in our previous sessions. However, we are now going to read this particular Fashion MNIST dataset, create dataset and DataLoader objects respectively. Also try and understand if the image data that you are trying to read basically is represented in the form of tensors or not, whether it's normalized or not. So data normalization is another key step that we are supposed to look at. Let's move on to this particular coding exercise. Here we have this particular fashion MNIST image classification problem that we are trying to solve now. So we have imported all the necessary libraries and modules. I've also turned off all the warnings so that whatever output that we are trying to observe is more legible. So I have tried to mount the Google Drive as well so that I can access whatever subdirectories that I'm having within my drive folder here. The very first step that I'm going to incorporate or implement here is to read this particular MNIST data by using this class called fashion MNIST. So within this particular parenthesis, I'm now going to provide the root directory into which I'm supposed to download my data. So root is equal to data. So I'm providing the subdirectory into which I'm planning to download the data. So I'm setting download is equal to true. So as to indicate that I want to download all the image files here. So while downloading, I also would want to transform the existing image data into tensor objects. So I can make use of this particular module called transforms here, which again is imported from Torch Vision package. So transforms.toTensor is going to help us convert this image data into tensor objects. So now I have converted this into tensor objects here. Cool. So whatever statement that I have written here on right hand side, I'm assigning to a new object called dataset. So this is nothing but it's an instance of this particular class called fashion MNIST. We clearly know about all of that. I also would want to create complete dataset by making use of the same class again. But this time around, I'm not trying to download anything, but I am necessarily going to create a dataset object specific to train set alone. Okay, let me copy this root directory as well. And I'm not providing any parameter called download. Instead of that, I'm providing train is equal to true. So as to indicate that I am trying to create a dataset object pertinent to the train data. So let me write a comment stating that this is going to be train dataset, or I can mention it as complete train dataset. I can also include an additional comment here stating that we are creating dataset objects now. Okay, cool. And again, I would want to transform this image data into tensor object. So I will also provide this particular additional argument. Once I complete this activity, I also would want to create a dataset object for test dataset as well. So setting train is equal to false is going to enable me to create a dataset object pertinent to the test set alone. Okay. So you can verify the length of each one of these. So you can look at the length of this complete dataset. It's the number of observations here, number of observations in the test dataset as well. So we clearly know that there are 60,000 different observations belonging to the complete data, complete train data, and there are 10,000 different observations that belong to test dataset here. So whatever train data that I have or whatever complete dataset that I have, I am now breaking this down into train and validation. So this here is going to be my train set. So this here is complete dataset. Complete dataset had 60,000 different records, 60K records. So I'm allocating a major proportion of it to train set. Probably like 50,000 observations I'm allocating to train set, and 10K observations I'm allocating to validation set. I already have this additional data set called test set. So this test set has how many number of observations? This test set already has 10K different observations. So my whole plan here is to create 3 different data sets, one of which could be train data set, which is for the model training process. So validation data set is purely used for hyperparameter tuning. I would want to find which of the combinations of hyperparameters that are present in my hyperparameter grid are more appropriate, or which of the combinations of hyperparameters are producing consistent results when it comes to train loss and validation loss that you are going to compute. Okay, so test set is left completely as unseen data. If you would want to extract an unbiased estimate of how good of a model that you have created, then you are not using test set for any of the training process. So you are leaving test set completely as unseen data. You're not touching it already, right? You're only making use of train set for model training process, validation set in the model training process, especially for hyperparameter tuning in order to find the right values for your hyperparameters. And finally, apply your model object onto the test set. Whatever model object that you create, you are going to apply it onto the test set try and perceive what the loss is or what the accuracy is. Try and compare the loss and accuracy that you have computed on validation set. If there is no deviation that you are observing, then whatever model that you have created is set to produce consistent performance on any given set. Okay, so this is purely to get an unbiased estimate of how good of a model is being performed. Okay, so since we have looked at creating the dataset objects already, now I am going to consider this complete DS and split this particular data into train and test datasets like we have discussed now. I'm going to make use of this random split function, which is imported from torch.utils.data. Okay, so random split, within random split, I am here providing the complete DS that we already have written within the parenthesis. Also providing the number of observations or proportion of observations that should be belonging to train set as well as validation set. Either I can provide proportions like I have provided now, or you can also specify the number of observations that you are planning to allocate to both train and validation sets here. So I'm planning to allocate 50k observations to train set and 10,000 observations to your validation set. Let me call them as train DS and valid DS, which is validation dataset. So length of train underscore DS, length of validation dataset is going to produce the number of observations that are present in each of these datasets here. So we have essentially created all the dataset objects. We have splitted this particular complete dataset into train set and validation set. Now you have train set, validation set, as well as test set here. We have all the three datasets that are required for conducting this model training process now. So the next step here is going to be creating the DataLoader objects. So we are going to make use of these DataLoader objects in order to iterate over batches of your input data. So whatever large number of observations that you have within your input data, we are going to iterate over all of the input data by batches. We are defining a definitive batch size here while creating the DataLoader object. So let me create something called train loader using this class called DataLoader class. Okay. So within the parentheses, I am trying to provide the respective dataset object that I already created in the previous step. Along with that, I'm specifying what my batch size is here. So batch size is a hyperparameter that we can look at tuning further. But for now, I have provided an arbitrary batch size of 128. So similarly, you can create a validation loader as well, which I'm calling it as valid loader, making use of valid DS batch size. Again, I'm retaining as 128. Let me also create a test loader object, provide test dataset object within this parenthesis here. Now you have created all the data loader objects associated with three different sets, train, validation, as well as test sets. Cool. We have never inspected how the data was looking, right? So we essentially have read the image data and tried to convert them into tensor objects straight away when you created the dataset object itself. But you have never tried to look at inspecting any of its elements. Now let's try to inspect what this 0th index would hold. So this 0th index will hold X and Y data. So let me unpack X and Y data here clearly. So my X data here is going to be a tensor object. You can see this is a tensor object. My Y data here is a label. This label can range anywhere from 0 to 9 as we have observed in the GitHub page earlier. Okay. So let me check the shape of this particular X data now. So what could be the shape of this particular X data here? The shape of X data is 1 by 28 by 28. So this is a three-dimensional tensor object, clearly, right? So we always thought that these grayscale images are generally represented in two-dimensional tensors. But for any of the given observations or for any of the images that are present within the data sets, you always have one for this particular dimension. So this represents channel here. This represents height and the width respectively. So this is a 28 by 28 pixel image. The height and width of this particular image is 28 pixel by 28 pixel. However, the channel that you are observing here is encoded with 1. So when it's an RGB image, when it's a color image, the value here is going to be 3. 3 by width, height by width, whatever it is, right? There could also be 4 different channels, especially when you are introducing the alpha transparency level as well. So then you will find a value of 4 for channel. Effectively, you have the associated height and width as well. I believe that you have understood the whole process here. So you need not explicitly provide an additional dimension in case of grayscale images. You can reshape this particular X data into a two-dimensional tensor. Because for each and every image, you'll have this channel value always depicted as 1. There's no point in it. So now I'm reshaping it to 28 by 28. So whatever data that I have reshaped, I've reshaped it into 28 by 28 two-dimensional tensor object now. Let me try to understand what this image is all about. I can simply go about importing matplotlib.pyplot, provide an alias to it. plt.imshow is a function that I can make use of in order to present this particular data in the form of a plot here. I can also provide a CMap stating that it should be a grayscale image. Let's also look at printing this result. So this here looks like a hoodie to me. This looks like a t-shirt or a hoodie, which I'm currently not able to perceive since the resolution is not that high. All the images resolution is very less. You only observe 28 pixel and 28 pixel on height and width respectively, right? So whatever it is, you are now able to understand or perceive the information that's being stored in the form of tensors here. I can also inspect other indices or other values for indices. So this should be X, right? This should be unpacked into X and Y. So let me use X here and reference index position 1. This is an ankle boot. The label associated with this should preferably be 9. It's 9 here. I was so sure about the label basically because I've gone through this particular tabular column where ankle boot is associated with this particular label called 9. Okay. So we have now looked at creating the dataset object and the data loader objects as well. And we have tried to read the image data and convert them into tensor objects. And finally, we also can understand how we can leverage this particular data loader object and try to iterate over this particular dataset batch by batch. So I'll now consider this particular train loader and iterate over this particular data loader object, right? And try to perceive what this particular data is all about. So you can always print the pair of X and Y that you're observing. I'll just try to break out of this particular loop after printing or after iterating for once. Okay. X here is clearly a 4-dimensional tensor object. So X dot shape here is going to be a 4-dimensional tensor object. Here there's an additional dimension. This represents batch size. We're now referencing the data loader object. We are not looking at accessing the data directly by using dataset object here. So we are making use of data loader object where we have specifically mentioned what could be the batch size, right? So the very first dimension here is going to be the batch size. This here is going to be channel. And this is height and this is width. I believe you are now understanding what each of these values within X dot shape would represent. Okay. So there are 128 different images that are being now read as tensor object here. Finally, you also observe that there is a particular tensor object which stores all the Y labels for the first 128 observations that we have read using this particular train loader object. Okay, cool. So now we are going to make use of these data loader objects that we have created and try and iterate over this particular data set and try and establish a particular training process now. And finally looking at finding the right values for your model parameters, that is weights and biases. We'll first define how the neural network architecture is going to look like. First define a custom model class and then further look at implementing the training process as a whole in our next sessions to come. Okay. In the previous session, we have looked at partitioning the given data set into train, validation, and test sets. So we thought of using the validation set in order to perform the hyperparameter tuning process. We also have left the test set as unseen data, so we get a true unbiased estimate out of it. Apart from data partitioning, we have looked at creating the data loader objects, which are generator objects, where you can iterate through or iterate over these data loader objects and get pairs of X and Y data. So the number of observations in each pair of X and Y completely depends on the batch size that we are providing. Essentially, when you read this particular data, in the previous step, you are trying to read the image data by itself. While reading the image data, you are converting all the images to tensor objects by using transforms.toTensor. So transforms.toTensor not only converts all of your images into tensor objects, it also normalizes the data. If you look at one particular observation that I read from trained data by providing an index value of 1 within the subscript notation. So if I look at the maximum and minimum value of x, so torch.min of x and torch.max in the parentheses I provide x again. So we clearly understand the minimum and maximum values pertinent to any given image or the complete data that we have. So we have this as 0 and 1. So whatever values that you are currently observing are bound within 0 to 1. So data is already normalized. I have not done any explicit data normalization as such, but I have made use of transforms.toTensor in order to convert all of my image data into tensor objects and also to normalize. Okay, cool. So while creating these DataLoader objects, please remember we're always setting shuffle is equal to true for train loader, and we're not doing this for validation and test loader, since we are anyways going to use a complete validation set and complete train set in order to evaluate the model that we have created. So shuffle is equal to true basically shuffles the data before you begin that iterative process. That's the whole essence of it. We need not shuffle the data since you're only applying your model object on validation. You're not looking at learning anything from validation or test sets here. Okay. So now let's begin writing this particular custom class called MLP, with which you'll be able to solve this multi-class classification problem. So we clearly understood that there were 10 different labels associated with your target variable, ranging from 0 to 9. So now, since this is a multi-class classification problem, I am going to create a model object. For creating a model object, I would need to write a custom class and then also need to define a loss function. The loss function here is going to be cross entropy loss, and then also define the optimizer object, which are essential objects for us to perform the model training process much later. Okay, let's write this custom class called MLP. MLP stands for Multi-Layer Perceptron. It's completely user-defined name that I'm providing. Let me also inherit all the attributes from nn.module, which is its parent class. So within class, I'm going to define this constructor method called init method, where I'm essentially providing the different parameters that one would expect while creating an object specific to this class. There could be in size, that is the number of neurons that are present within your input layer, hidden size as well as output size, calling it as out size in short. I'm also using super in order to initialize my parent class here. So within parentheses, I'm providing the current class and self here. So now I have initialized my parent class as well. So obviously I'm going to now define the different layers that are present within my feed forward neural network. Okay. The first layer here I'm going to define here is going to be hidden layer. So it's nothing but a linear transformation of inputs and weights that you receive from your preceding layer. nn.linear, the number of inputs that it would receive will be nothing but in size. The number of outputs that it's going to generate will be hidden size. So this is my hidden layer. I'm going to define the output layer as well. The input for my output layer is going to be the output from its preceding layer. Output of my output layer here is going to be nothing but the out size. So once I define these layers, I'm also going to create a forward method which expects the X data. Okay. Now, whatever data that you are currently observing, so whatever X data that you have previously looked at this three-dimensional tensor, or there are three different dimensions associated with it to be more precise. The first one would represent the channel. The second one would represent the height. The third one would represent the width. So 28 by 28 pixels is what we are currently observing. Since this is not an RGB image, since this is a grayscale image, we always observe 1 for channel, a value of 1 for channel. So whenever you are having RGB images, you will have a value of 3, one representing each one of these channels, 1 for red channel, 1 for green, and 1 for blue channel. If it's in RGBA format, where you are also including the alpha transparency level, then you'll have 4 per channel here. So it doesn't make any sense to me to include this at all, since it is pretty much the constant value of 1 for all of the grayscale images. I would like to convert this into a 2D image, or more preferably, I would want to flatten this image out into a one-dimensional vector. So that's what I'm perceiving currently. Right? Let's say that This is a 3 by 3 image. So 3 pixels height and 3 pixels width. This is a hypothetical scenario that I'm currently considering. In our case, we have 28 pixels height and 28 pixels width. But if this is a 3 by 3 pixel image for simplicity, so we are now having total about 9 pixels in the image. I'm looking at flattening this particular image out completely, converting this into a vector. Whatever 3 pixels that you are currently observing in your first row will now be part of this. Okay? Whatever second row pixels, 3 pixels that you have in the second row will now be part of this here. The third row will have these 3 different pixels which are appended to first and second row pixels. So this is a 1D vector. So I am now converting this to a vector of 9 different elements here. So essentially I'm going to convert this grayscale image into a vector with 784 different elements. So 28 multiplied by 28 is going to result in 784. I believe you have understood. So similarly, I would also want to convert this particular X data, right? Or reshape this particular X data using view or reshape method into vectors, the images into vectors. So -1 here, by providing -1 here, I am just informing PyTorch to consider as many number of images that I'm receiving in X data and use that number as one of the dimensions. Let's say that my batch size is 128. Now in my X data that I'm going to make use of while invoking forward method, essentially I'm going to reshape this X data. The dimensions for X data or the shape for X data currently will be 128 by 1 by 28 by 28, right? Now I am planning to reshape this into 128 by 784. So -1 indicates that consider as many number of data points or as many number of observations that you are receiving as is, but only transform these images or convert these images into one-dimensional tensors. That's what I'm doing here. So 28 multiplied by 28 multiplied by 1 is going to result in 784. So I'm assigning this to a new object called xb. Okay. I'm going to make use of this new object or this new data xb, which is a reshape data, as input to my hidden layer. And obviously I'm also passing this to this particular activation function called ReLU activation function. Okay. So torch.ReLU is what I am going to make use of in order to generate an output Z1. Okay. So whatever output that I receive or generate in my hidden layer, I'm going to make use of that as an input to my subsequent layer, which is going to be self.output. I'm providing Z1 within the parentheses. So whatever resultant values that this output layer is generating are nothing but the raw logit values. I'm not applying any softmax activation function yet. We are supposed to use softmax activation in case of multi-class problem. We already know about this, right? But I have not applied any of these activation functions. I have not applied softmax activation yet onto these raw predictions or raw logit values that I have deduced so far. I'm leaving it as is for now because the cross entropy loss expects this raw predictions or raw logit values itself, because it implicitly does the transformation or it implicitly applies that sigmoid function. Sorry, it implicitly applies that softmax activation function on all of these values here. Cool. So instead of defining these different layers and using these layers internally again within the forward method here, I would like to create the network as a whole. So let me create the network and call it as self.network using nn.sequential class. So nn.sequential class helps us create this network at once. So I'm going to provide nn.linear for my hidden layer first, nn.ReLU, which is my activation function that I'm applying on the resultant transformed output that I have from nn.linear, the hidden layer 1. And finally, I'm also looking at providing output layer, which considers hidden size as my as a number of inputs for it. And out size here is going to be the number of outputs that it would generate. So we already have created this self.network. I'm going to make use of this directly instead of these two different steps. I'll now have only one step where I provide XB data that I already have reshaped in my previous step. This here is going to generate the same values, which is nothing but the raw predictions by itself. So we can instantiate this class now by providing all the necessary arguments in size here is going to be 784. After flattening an image, you will have 784 different elements within your vector. That is 784 different inputs that you are passing to your hidden layer one. So I'm providing an arbitrary size for the number of neurons that I'm planning to have in my hidden layer, which is going to be 100 here. Outsize is pretty much predefined. Since there are 10 labels, I would generate 10 different values. Okay. So I'm calling this object as model. Let me also define the loss function, which is the cross entropy loss. I'm not using binary cross entropy. This is not a binary class problem. This is a multi-class problem. So I'm going to make use of cross entropy loss. So this is the loss function here. I'll also create the optimizer object. So optim.sgd is a function that I'm going to make use of. Necessarily going to provide model parameters here. And once I provide model parameters, I'm also providing this hyperparameter to hold an arbitrary value of 0.001. Please remember, all of these are hyperparameters. The learning rate here is hyperparameter. The number of neurons for my hidden layer is going to be another hyperparameter. And even the batch size that we have defined while creating these DataLoader objects are also again going to be hyperparameters. We'll later see how we can perform hyperparameter tuning by considering range of possible values for each one of these. Okay. So we now have created all of these different model objects or all of these different objects, model object, the cross entropy loss function, as well as the optimizer object. We can make use of this particular object, model object, and invoke this forward method and provide the X data. If you observe carefully, X data currently is only pertinent to one single observation. So if you look at this particular step, I am referencing one particular image with index 1 in my train set. Okay? So I'm making use of this X data. I have not yet implemented the model training process yet, wherein we iterate over the DataLoader objects. I have not done that yet. But I'll make use of this X and Y data so as to understand how the raw outputs would look like. Okay. So model.forward of X is going to generate all the raw predictions or raw logit values here. So if you observe carefully, these are the logit values. I'm going to make use of all of these predictions that I have, or raw predictions to be more precise. I'm going to make use of all of these raw predictions and pass it to torch.softmax in order to generate the equivalent probabilities associated. So now this here is going to generate different probabilities associated with all of these labels. So we clearly can understand that 0.1144 is the maximum of all the values that it generated. And if I am going to make use of these predictions that I have done, let me call these as predictions. I'll make use of these predictions that I have now computed. Use torch.max function. I'm just trying to derive which of these predictions is having a maximum value and what is the label associated with it. Calling it as spread label. Okay. Now let me print these two different values so as to understand what is the maximum value and predicted label. The maximum value should be 0.1144 and the predicted label should be 9. Okay. So the maximum value that's returned here is 0.1144 and obviously the predicted label is going to be 9 since we clearly know the labels start from 0, 0, 1, 2, 3 and so on till 9. So the maximum value we are observing at this 9th label. So we have the predicted label as 9. So let us look at what the actual Y value is for that particular index position 1. The actual Y value is 7. And this is a misclassification. Obviously, it's going to be a misclassification since we have not begun the training process yet. Whatever weights and biases that we have initialized at the very first step. So we have not even updated our weights and biases at least once here. So obviously the performance of this model, whatever we have created, is going to be very poor unless we actually iterate or unless we actually implement the model training process more efficiently, like conducting it for n number of epochs. Okay. And within each epoch, you'll have multiple iterations to conduct depending on the batch size that you're having. So we have not implemented any of that process yet. So we're going to discuss in detail on how we essentially implement the multi-layer perceptron model or implement the training process as a whole by considering all of these different objects that we have created so far. Okay. So far, we have done the data partitioning, we have done the necessary data pre-processing, created the dataset DataLoader objects, We also have created the custom class, which is MLP. So we have instantiated this class to create the model object. We later have defined the loss function, which is the cross entropy loss, and also created the optimizer object. We looked at one particular prediction by conducting one forward pass and also observed what its maximum value is and what its corresponding predicted label is. We understood that it's a misclassification since we have not essentially implemented the model training process, which we are going to conduct now. So we'll have to conduct multiple epochs. So I'm going to write an iterative for loop for epoch in range of 100. So this is an arbitrary value again. So this here could be another hyperparameter. I'm providing a value of 100 for now. So that is, we are conducting 100 different epochs in this whole exercise. For each epoch, we are going to iterate over the existing train loader object, which is a generator object, right? So iter and then train loader. So this here is going to generate pairs of X and Y. We are going to iterate over batches of X and Y data, each batch comprising of 128 number of images that we already have transformed into tensor objects. Okay. And the normalization also is applied on that. Cool. So for each of these X and Y data, we're now going to conduct a forward pass. Let's conduct a forward pass using the X data here. So whatever predictions that we are generating from our forward pass are nothing but the raw logit values. We are later going to make use of these raw predictions, apply softmax in order to derive what the predicted probabilities are. Later assess which of these possible values or which of these possible logit values or predicted probabilities have got a maximum value. Whatever the label associated with that maximum probability value is going to be my ypred. Okay, that's what we have thought about, but we're not implementing that yet. So we are now looking at computing the loss. So the loss here is going to be P loss. Within the parentheses, we are providing the logit values as is. We're not converting them to probabilities yet. Since the cross entropy loss function has got this implicit conversion to probabilities, so it implicitly applies this softmax activation to all of these logit values. So we'll also pass the y labels, whatever y data that we are observing. So we are passing the actuals as well as predicted values while computing the loss. So here we have conducted the forward pass. Okay, here we have understood what the loss is. Now we'll implement the backward propagation as well. So in this step, we are doing backward propagation. So once the backward propagation is done, once all the gradients are computed, now you look at updating the weights and biases using step function. Update weights and biases in the complete network. Cool. So once the weights and biases are updated, we'll zero out all the gradients as a regular process. So once all the necessary steps are implemented, we now need to evaluate our model at the end of each epoch. So at the end of each epoch, I am planning to evaluate the model, which essentially means that I'm planning to compute what my validation accuracy is and what my test accuracy here is going to be at the end of each epoch. Okay. Evaluate is a new function that we need to create, which actually accepts two different arguments, one of which is model object as is. The other one could be the validation loader in our first case, the data loader object. In the second case, it's going to be a test loader object. Cool. So, but we have not defined this evaluate function yet. So let's define this evaluate function, and we are going to define two different parameters, model as well as test loader. So I'm just providing an arbitrary name test loader. This here could be validation loader whenever we execute this statement, and this here could be test loader whenever we execute this statement. Okay, so it's just the name of the parameter. You can change this to any other name that you prefer to have. Okay, so now for each of X and Y pairs that I deduce from the test loader here, which again is a generator object, right? So obviously I am going to make use of this model that we already have received as a parameter and execute the forward pass here. When executing the forward pass, providing X data within the parentheses, now I am getting the raw predictions here. So whatever raw predictions that I got, if I am applying softmax on it, I'm going to generate the predicted probabilities. I'm also going to understand what my predicted label is by using torch.max function by providing the predicted probabilities that I have derived in the previous step. We have learned about this pretty much, right? Within each of these inner for loop, I am now looking at understanding how many of these observations are correctly classified. So the number of cases where pred labels is equivalent to the actual wise here. Take the sum of it. Now I'm taking a cumulative sum. Since this is in a for loop, I'm taking a cumulative sum and assign it to something called correct. So correct is equal to correct plus number of correctly classified points within each of these iterations that we are conducting. So let me initialize this new variable called correct to 0. Also initialize a new variable called total here. So total is going to be the total number of observations that we have evaluated. That is equivalent to number of images that we have processed in each of these iterations. So once we have completed the inner for loop, once we have completed the for loop, once we have exhausted all of the data, now we look at how many number of cases did we correctly classify of total observations that we have evaluated. So correct by total multiplied by 100 here is going to be nothing but the accuracy. I'm going to return the accuracy here. And that's it. This is my evaluate function. So evaluate, provide the model as well as the relevant data loader object so as to derive the associated accuracy. I'm calling it as validation accuracy and test accuracy respectively. Okay. But I'm just missing out some points here, right? So within each epoch, we are conducting multiple iterations. So at the end of each epoch, we are now tracking validation accuracy as well as test accuracy, which is good. So instead of running 100 different iterations or 100 different epochs to be more precise, let me run only 3 epochs for now. Okay. Let me also provide TQDM notebook so as to understand the progress of it. So while it runs, we can necessarily capture all of this information in a resultant data frame. So I'm going to create an empty data frame here called result. So whatever we have captured, whatever validation accuracy, test accuracy that we have captured so far, I now can actually write it to a particular data frame. So pd.data frame. And within this subscripts, I can provide the epoch number, the validation accuracy, as well as test accuracy here. Okay. So I can concatenate this with the empty data frame that I have created right before beginning of the first epoch. So I am trying to concatenate this with the result data frame and assign it to result back so that I capture each and every epoch and its relevant validation and test accuracies here. Let me end this whole process and let me rerun right from this step so that the weights are reinitialized. And now we can go about renaming the column names. The first column name here is going to be epoch. Second column name could be the validation accuracy, and third one could be the test accuracy. Print out the result as well. So once the result is printed, now you also can come up with a figure and axis, or can also come up with a plot to be more precise. Using plt.subplots function, you create figure and axis objects. ax.plot on x-axis, now you can come up with epoch, and on y-axis you can have the validation accuracy. And obviously I can provide a label so as to indicate this belongs to validation set. Similarly, I can also present what my test accuracy is, but label should be test here. ax.legend is going to display the legend for me, and obviously plt.show is going to display the plot. But I would also want to set the x label. X label here is going to be epoch. Size of it, the font size of it is going to be 14, which is arbitrary again. I can also set the y label here. Y label here is going to be accuracy. That's all. So we now have the result data frame ready. So we clearly know the validation accuracy for epoch 1 was 35.05. Test accuracy was 34.96. But these are not numeric in nature. So I would have to include or change this to dot item so as to reference the actual values. Not done in the past. So now I am correcting that particular statement so that now you have proper representation of validation and test accuracies for each of these epochs. So we clearly know the accuracy is increasing epoch after epoch. And the deviation that we are observing between validation and test accuracy also is not that significant. Okay, but we need to conduct like n number of epochs. So we cannot restrict ourselves to only 3 different epochs. We need to conduct this whole iterative process probably to 100 different epochs or more. Again, as I have mentioned to you earlier, number of epochs is going to be a hyperparameter always. So we always need to actually perform hyperparameter tuning so as to understand what could be the right value for number of epochs. We also have come up with a plot here. Okay, but this is not sufficient. The number of epochs that we have conducted is not sufficient. If we are updating this number of epochs from 3 to 100, it's going to take a lot of time. The processing or the model training process here is going to take a lot of time. So it's not worth to actually implement this process on CPUs. And that's when we need to push our relevant data and model objects onto GPUs and then do our model training process on GPUs so that the runtime will speed up. Overall runtime that we might end up with is significantly lower in when you are using GPUs over CPUs. So that's what we are going to discuss next. How do we retrofit this particular code to actually push our input data and different model parameters or model objects onto GPU and then do our model training process on GPU rather than on CPUs? Look at it here. I've not connected to GPU at all yet. I can change my runtime type and I can select T4 GPU. So it switches from CPU to TPU here. Sorry, CPU to GPU here. Okay. So that's what we are going to discuss in our next session. During our introduction sessions, we have understood the difference between using a CPU and using a GPU. We also have understood what a TPU is, which stands for tensor processing unit. As we have learned initially, GPU basically consists of these hundreds of different simpler cores, which are optimized for performing these complex matrix operations. When I say matrix operations, it's nothing but the tensor operations. All of these linear transformations that you are doing in your forward pass are nothing but the matrix operations here. So the model parameters here are going to be weights and biases, which are represented in the form of tensors. All your input data, X and Y data, are again represented in the form of tensors here. So you make use of this data loaders that you have created in order to read the complete data batch by batch. So every pair or every batch of X and Y data are now represented in the form of tensors. So how do you make sure that you are implementing the overall model training process on GPUs, that is using GPUs than using CPU now? If you are going to check the type of this particular tensor, whatever device of this particular tensor to be more precise, it's going to be CPU now. So X here is going to be the input data specific to an observation in my train set. If you observe carefully, so you are referring to one of the observations or one of the images pertinent to your trained data set. I'm just unpacking it into X and Y. X here is going to be a tensor and Y is going to be a label, which preferably is an integer in nature. So now the device associated with this particular input data X here is going to be, it's going to be CPU, right? So since I'll have to rerun this particular code so as to make sure that I'm not saving any of my previous memory here. Cool. So you clearly know that the device is now pointed as CPU. Okay. So I am now going to update this particular or move this particular input tensor onto GPU using this interface called CUDA. Okay. Or the device type here is going to be CUDA instead of CPU. As we have learned earlier, NVIDIA GPUs basically has this application programming interface called as CUDA, with which you interact with all of the GPUs that you are provided access to. Okay, cool. So now I need to move all my input data, all my XY data to GPU using this device CUDA. Okay, or interface CUDA to be more precise. Move all model and model parameters to GPU again using CUDA. So these are the exercises that we are going to conduct now. So how do I move all of my X and Y data? So I am reading my X and Y data batch by batch using data loaders. So I'm going to make changes to my existing data loader, the way in which I'm retrieving the data batch by batch. I'm going to make some change there. So that as and when I read X and Y data, I'm going to move them to a GPU. Or preferably I can simply go about writing a custom data loader class which does the job to me. Okay. But anyways, before doing all of that, let's look at the availability of the GPU for us. I have connected to T4 GPU by changing the runtime here. So I have switched from CPU to T4 GPU here. I've saved it so that now it's pointing to GPU. Okay. So torch.cuda.is available actually helps us understand if we are connected to a GPU or not. If this returns a Boolean true, this indicates that the device CUDA is available to us. So I can simply write a user defined function, call it as get default device. So I'm just planning to write a device agnostic code here. So be it CPU or be it GPU that your code is currently pointing to, it should be able to run without any errors at all. And hence we are customizing our code in a way that it will not break or it will not error out, even if it's GPU or even if it's CPU that we are pointing to. Okay. So if CUDA is available, then we are going to return torch.device, which is nothing but CUDA here. So we are going to return a device object which points to CUDA. If it's not true, if it's false, that essentially means that we are running on CPU. We are going to return a device object which points to CPU now. I simply can invoke this particular function so as to understand if it's pointing to CUDA or CPU now. So it points to CUDA. Okay, I can call this as device now. You can also print so as to understand the contents of this particular newly created object here. Cool. So whatever X data that you had, you can access this particular method called to and provide device within the parenthesis. This essentially is going to move or push your data onto GPU. I can reassign this back to X and check for the device now. So before executing this particular statement, check for the device. After executing, check for the device. Now you clearly understand this particular to method is helping us to move our tensor objects onto a given device. The device being saved as CUDA from our previous step, since we are able to access the GPUs here. Cool. So this is the whole process that we are trying to implement for the given data loaders. So we're now going to write a custom data loader class. So all of the data loaders that we have created earlier, be it train loader, validation loader, or test loader, all of these data loaders are nothing but generators. So there are two primary methods for generators, one of which is going to be the item method as well as the alien method. We are going to do method overriding in our custom class definition that we are going to have now. So class custom data loader is the name of the class that I'm going to provide now. So within this particular class, I am going to define my init method first. Init method will have self data loader as well as device object. So self.dl is going to be DL itself, self.device is going to be device itself. I'm attaching both the data loader and device to the object of this particular class itself. And then I'm going to define the underwriter, so which is method overriding that I'm planning to do now. So within parentheses, let me provide self. Now I'll be able to access self.dl and self.device within this particular iter method here. Okay. So let me make use of this particular method and write this particular code, which essentially iterates over the X and Y data that you are having in each and every batch that you are reading. Okay, so for B in self.dl, this indicates, B here indicates the batch that you are planning to read, that is X and Y both, a tuple of X and Y. So I am just writing a simple list comprehension, writing it as D for D in B. So every X and Y, be it X or Y, doesn't matter. I'm going to access this to method and move it to GPU. I'm providing yield since this is going to be a generator object. That's it. I'm also going to do a method overriding for alien method. So essentially, I'm not going to change any much of a functionality here. I'm just going to return the length of this data loader. That is the number of batches that it's going to iterate over. Okay, that's all. So alien of self.dl is going to return the total number of batches that are available as part of this particular data loader object. Cool. So we have now defined this particular custom class called custom data loader. I'm going to make use of the existing train loader that I already have created previously and also provide the device object and then reassign this to train loader here. Same is the case with test loader as well as validation loader. So test underscore loader is in the second statement. So valid underscore loader is going to be in the third statement here. So we have updated the code by wrapping this custom data loader to your actual data loader objects. So all what we are trying to do here is to move your pairs of X and Y data or batches of your X and Y data onto GPUs by using this method called to. Instead of writing all of this class, you simply can go to this model training process where you are reading this x and y data, you can simply do x dot to provide the device here, y is equal to y dot to provide the device here. It really doesn't matter. So you need not write this whole custom class like we have written here, but this is for the structured programming that we are doing, right? So this is always a good practice to do in this manner. For now, I'm just getting rid of these two different statements that we have written for illustration purposes. However, since we already have updated all the data loader objects now, we are looking at implementing the model training process again. So as to understand what is the improvement in the overall runtime that we are having by using GPUs and by not using GPUs. Okay. So before we do that, we'll also move the model object along with its parameters to the GPU by using this particular method called to. So within parentheses, I'm going to provide the device object which points to CUDA now. Cool. So let me rerun this particular code, recreate all of these objects, rerun this evaluate function definition, rerun this whole training process, and let's keep track of the total time that it takes for completing all the 3 epochs that we have planned to complete now. Okay, and compare it with your previous iterations or previous model training process that you have conducted. So there will clearly be a difference in the overall runtime. The difference might not be significant because the model architecture here is not that complex. The difference in the overall runtime is very much prevalent, especially in cases where you are having complex architectures like multiple hidden layers, or probably in your convolutional neural nets where you have additional layers in between, right? So that's not the case here. However, you can verify the overall runtime that it has taken when you are using GPUs versus when you are using CPUs, and clearly note the difference there. Okay, so we have retrofitted the complete code in order to move all of your input data to GPUs using CUDA, and also moved your model along with its parameters to GPUs, and finally implemented the model training process again. And look at the results and go with plotting the results again. So in the next session, we are looking at performing hyperparameter tuning. So this code remains the same for any of the models that you are going to create in future. So you can make use of this code that we have written, where we are implementing this custom data loader class. We are recreating the data loader objects by using this particular class. So this code remains the same. You're not going to change them. Whatever model it is, whatever complex it is, there might be some subtle changes, but pretty much it remains the same. Cool. In the next session, we are looking at performing hyperparameter tuning and also try and understand which possible combination of hyperparameters is going to produce good result and consistent results when you compare your validation accuracy with your test accuracy, or validation cross entropy loss with your test cross entropy loss here. Okay. So far, we have looked at solving this particular image classification problem by considering specific set of hyperparameters during the model training process. So all of these hyperparameters generally had some fixed constant values. Like we have considered a value of 0.001 for learning rate. We have considered batch size to have a value of 128 and all. So specifically when we have created the data loader objects, we only have considered a batch size of 128, which was fixed in nature. So we essentially have also looked at considering other hyperparameters to have fixed values like the number of neurons that we can define within the hidden layer, so on and so forth. I don't want to get into all of these details, like what are the different hyperparameters and what are the different values that we have considered for our previous model training process. But what I would want to stress upon here is to conduct the hyperparameter tuning. So conducting hyperparameter tuning is one of the critical steps in model building process. So we cannot simply go about considering some arbitrary values for different hyperparameters and then create a model. We need to evaluate all possible combination of hyperparameters and try and identify which of those combinations is going to result in a model that performs better. Not only provides good accuracy, but it also provides consistent results on validation set as well as test set. Speaking about validation and test sets, we initially have partitioned our data. We have partitioned our data into train set, the validation set as well as test set. We had equivalent number of observations for both validation set as well as test set during the data partitioning exercise. Okay. So we thought about considering the validation set purely for hyperparameter tuning purposes. So we consider this validation set only to evaluate which of these hyperparameters is going to result in a good performing model. And we thought about leaving the test set completely as unseen data, so we get a true unbiased estimate out of it. Whether the accuracy that we obtain over the test set, whether it's close enough to the validation accuracy that we have obtained for a given hyperparameter that we have finalized. That's the whole exercise that we plan to conduct. Now, let us first define the hyperparameter grid and implement the whole hyperparameter tuning process. So let me define a new dictionary called hyperparam grid, which considers different hyperparameters that we are planning to tune. The very first hyperparameter that I'm considering is learning rate, wherein I'm providing some possible values here, like 0.001, 0.0001, and e to the power of -5, some arbitrary values. I'm also providing batch size here. So the possible values for batch size could be 32, 64, 128, so on and so forth. I'm only considering two different hyperparameters for simplicity. You can expand this hyperparameter grid to any possible number of hyperparameters that you would want to fine tune within your model training process. Also provide a possible range of values for the respective hyperparameter that you are considering, just like what we have done for learning rate and batch size here. So hyperparameter grid dot items is going to result in key value pairs to me. So I would want to unpack this items of this particular dictionary into keys and values. So star here is the unpacking operator. I just wanted to zip the items so that we extract keys and values accordingly. So keys and values are nothing but the keys of this particular dictionary, which are nothing but the learning rate and batch size. Values here are nothing but the list objects. So the first list object is associated with the learning rate, the list of possible values that we need to search for learning rate. The second list object here is going to be the possible values that we need to search for batch size here. So this is associated with batch size now. So once we have extracted all of these values, so we want to actually find the Cartesian product of all these hyperparameters as stated above. Right? So how do I find the Cartesian? Cartesian product is nothing but finding all possible combinations. The first combination here could be for the first value of learning rate, we take the first possible value within batch size. So this is one combination. So 0.001, 64, this is second combination. 0.001, 128, this is third combination. So once all of these are exhausted, you pick up the subsequent value within learning rate, that is e to the power of -4, e to the power of -4, 32, e to the power of -4, 64, and then with 128. So you just try to construct all possible combinations of this hyperparameter grid, which is nothing but the Cartesian product here. So here I am going to consider whatever values that I have obtained in the previous step. And now I'm going to make use of itertools.product, which is going to result in the Cartesian product that we are looking for. So I would import the itertools first, itertools module. And then for every possible value that I read, so I just write simple list comprehension, v for v in, that's all. So v for v in itertools.product, within the parentheses I write values here. So star here is unpacking operator, as you already know. And while presenting the values to the user, so while I present these values to the user, I also would want to combine these individual tuple values that I'm observing with keys as well. So I would zip the different keys that are available and the values that are available. Okay, because so this corresponds to LR and this value corresponds to batch size here. That's why I would want to zip both keys and values that I'm observing for every product within the Cartesian product that we have derived. So now I would wrap this as a dictionary. So I'm storing the result in a list object as different dictionary objects. So for every possible combination of hyperparameters that are derived from the hyperparameter grid are now stored in the form of dictionary objects. So I'm going to make use of this particular list called params in performing my model training process. So I'm going to make use of this particular list object in my model training process. Speaking about the model training process, I'm going to consider this whole code that we already have written. I'll paste it here. Now I'm going to write an outer for loop for param in params that we have determined in the previous step. For each of these parameter combination, I'm going to conduct this model training process now. But instead of providing some fixed and constant values for learning rate and batch size, I would infer the batch size and learning rate values from the individual dictionaries within this inner for loop. Okay, so let me consider recreating the data loader objects that we already have created. So we navigate to this particular step, copy this whole code, and then recreate all these data loader objects, train, validation, and test loader. But instead of providing this arbitrary value of 128, now I actually provide this particular, or I actually provide a reference to this batch size pertinent to this particular dictionary that we are actually reading from the possible combinations of the parameters from this given list. So I'll replace this 128 with the reference to batch size in the given dictionary. So this is the dictionary that I am currently on in the first iteration, right? So instead of hard coding the value as 32, now I am referencing the value by providing the key within this subscript notation, the key of that particular dictionary within the subscript notation. I would also want to update the data loader objects since I'm now pointing to GPU here. So custom data loader is a class basically which pushes all of your batches of X and Y data onto a specific device being GPU, as we already have defined it in one of our previous steps. So once all the relevant data loader objects are defined, now is the time that we go about creating the model object, push that particular model object onto the GPU device. Along with that, we also define the loss function as well as the optimizer object. And then instead of computing the validation accuracy and test accuracy at the end of each epoch, now I would want to compute validation and test accuracies at the end of each parameter combination evaluation. Okay. So along with validation accuracy and test accuracy, I would want to compute what the train accuracy is by providing train data loader object within the parenthesis as an argument while you invoke this function called evaluate. So I would also try to keep track of the accuracy obtained on train set within this particular result data frame here. At the end of the whole process, I would define the column names. So I also would want to include the dictionary of parameters as such so that I would understand what are the corresponding learning rate and batch size values for the different evaluation metrics that we have tracked. Okay. So I'm providing the column names in this particular step here. The first column name is going to be the parameter dictionary. Here it's going to be the epoch, the maximum epoch value that we have obtained so far. And then train accuracy, followed by validation and test accuracy as well. So instead of providing the number of epochs as 50, I would provide the number of epochs to be just 2. So this is just to reduce the overall runtime. For a better explanation to you, I am reducing the number of epochs from 50 to 2. But I would strongly encourage you to have the number of epochs as an arbitrarily higher value like 100 or 200 or 500 and then implement early stopping criteria. So I would ask you to implement early stopping within this particular block of code. Implement early stopping by providing an epoch value to be probably 500 or 1000. It really doesn't matter because if the validation accuracy is not improving in your iterations that you are conducting or in your epochs that you are conducting, to be more precise, if it's not improving, then you are going to end the training process then and there. You're not going to conduct the remaining epochs at all. I would strongly encourage you to incorporate or retrofit this particular code to implement the early stopping, as well as update this number of epochs that I'm providing here as 2 to 500 or 1000. Okay. So let me run this whole process. Let me run this whole code. And this is a progress bar that we are showing. It's clearly stating that there are only 2 epochs that it's conducting for every parameter that we are trying to evaluate. For every parameter, we're now going to conduct only 2 epochs. So once this is done, so there are 9 combinations in total. There will be 9 progress bars that will be shown now. So once this whole training process is done, I would want to arrange this particular data frame. I would want to sort this particular data frame by the validation accuracy arranged in descending order. So ascending is equal to false here. All what I'm trying to do here is I'm just trying to identify which of these parameter combinations resulted in a lesser deviation between train and validation accuracies. At the same time, whatever accuracy that I have obtained on test set, whether it's close enough to validation accuracy or not. So that's the expectation. So whatever test accuracy that you obtain, we expect it to be pretty much similar to the validation accuracy. At the same time, we also would want to see the deviation between train and validation accuracy so as to understand whatever model that we have created, whether it's generalized in nature or not. So all what we are trying to do here is we are trying to create a model object which is much more generalized in nature. Along with that, we are also trying to understand that the model does not have any overfitting or underfitting by validating the unseen data or test data accuracy, comparing it with validation accuracy. Okay. So we finalize one such hyperparameter combination that's going to provide us a very high validation accuracy and a minimal deviation between train and validation. And we also would want to do an additional check on the resultant unseen test accuracy, whether it's close enough to validation accuracy or not. So this is a whole exercise that I would want to strongly encourage you to conduct. Okay. I'm leaving this as an exercise since this is going to take a pretty good amount of runtime. And finally, I would want you to inspect how the results would come out. Okay. So that's pretty much all I wanted to discuss with you in this session. Thanks for watching.